United States Provisional Patent Application. Buckyball-stabilized superfluid vortex gyroscope. Inventors: Chris D. Seely Yocum. Filed May 2026. Cross-reference: continuation in part of QLAG System, Seely and Yocum, May 2026. Attorney Docket No. Cross-reference to related applications. This application claims the benefit of priority to and incorporates by reference in its entirety the co-pending provisional application entitled Quantum Lagrange Array Gravitational Interferometer, filed May 2026 by Seely and Yocum. All definitions, figures, and enablement disclosures in QLAG are adopted herein. Where QLAG describes a BEC-MASER station, Josephson junction pair, parametric transducer, or Lagrange-point operation, those descriptions are incorporated as if fully set forth. This application is filed as a continuation in part of QLAG to preserve the May 2026 priority date. Field of the invention. The present invention relates to quantum inertial sensors for deep space navigation and high maneuver vehicles. More specifically, it relates to a superfluid helium-4 gyroscope wherein a single quantized vortex is stabilized by a single fullerene molecule trapped in the vortex core. Axially confined by a resonant second sound standing wave, and read out by an integrated superfluid Josephson junction phase locked to a Bose-Einstein condensate maser frequency standard as described in QLAG. Intended fields of use include deep space spacecraft, lunar and planetary landers, high-agility defense platforms, and any application requiring autonomous inertial navigation without dependence on GPS or ground-based tracking. Background of the invention. Precision inertial navigation currently relies on one of three technologies, each with fundamental limitations. Ring laser gyros achieve angular random walk of approximately 8 × 10 deg/hour and bias drift near 1 × 10 deg/hour, bounded by shot noise in the optical cavity and long-term drift of the mechanically stabilized mirror mounts. Fiber optic gyros perform similarly, with ARW near 5 × 10 deg/hour and bias near 5 × 10 deg/hour, also constrained by photon shot noise and the backscatter characteristics of the fiber coil. Both technologies saturate at a few hundred degrees per second, limiting utility in high-agility applications. Cold atom interferometers reduce ARW to approximately 1 × 10 deg/hour by exploiting the de Broglie wavelength of laser-cooled atoms. However, their measurement bandwidth is below 1 Hz, and the laser, vacuum, and magnetic shielding subsystems required exceed 100 kg in current implementations, making them impractical for most vehicle applications. Superfluid Josephson gyros have been predicted, from the fundamental Sagnac phase relationship for superfluid helium, to offer sensitivity 10 to the power of 1 times greater than ring laser gyros. Prior experimental work confirmed the Josephson phase mechanism but did not demonstrate a stable, repeatable vortex marker capable of surviving operational vibration, nor a readout architecture that avoids the need for an independent atomic frequency standard on the vehicle. QLAG discloses BEC-MASER stations at Sun-Earth Lagrange points L1 through L5 with fractional frequency stability of 10 to the power of 6 at 1000 s integration time. Superfluid Josephson junction pairs with demonstrated magnetic sensitivity of approximately 10 to the power of 8 T. A parametric transducer with interaction Hamiltonian H-int equals G for phase-preserving quantum coupling, and force-free gravitational operation at Lagrange points with residual acceleration below 10 to the power of 5 meters per square second. No prior art combines a single fullerene vortex marker, second sound axial stabilization, and Josephson readout phase locked to a BEC-MASER into a unified sensor architecture. Summary of the invention. The BBG-SVG comprises 5 cooperating elements that together constitute a complete quantum inertial sensor. Superfluid He2 reservoir. A superfluid helium-4 volume maintained at 1.5 to 1.8 K, well below the lambda transition temperature of 2.1768 K, forming the Sagnac loop medium. Quantized vortex with fullerene marker. A single quantized vortex line with circulation kappa equals h per meter He, with one C60 molecule trapped in the vortex core by the Bernoulli pressure gradient, serving as a topologically stable, spectroscopically verifiable phase reference. Second sound axial resonator. A second sound standing wave cavity aligned coaxially with the vortex, driven at resonance frequency Fn equals Nc2, 2L, where C2 approximately equals 20 meters per second at 1.8 K, providing contact-free axial confinement of the fullerene to below 10 nanometers positional uncertainty. Integrated Josephson readout. A superfluid weak link aperture of 50 to 200 nanometers intersecting the vortex line, coupled to a DC squid fabricated on the same substrate, transducing the Sagnac phase shift directly into a squid output signal. Phase lock to QLAG BEC-MASER. A phase lock loop referencing the second sound drive and the squid local oscillator to the QLAG BEC-MASER carrier frequency, eliminating the need for an independent frequency standard on the vehicle and conferring 10 to the power of 6 fractional stability on the rotation measurement. The resulting sensor achieves angular random walk of approximately 2 times 10 to the power of 8 deg square root hour. Bias stability below 1 times 10 deg per hour, bandwidth from DC to 1 kHz, maximum sustainable angular rate to the power of 9 of 2.86 times 10 to the power of 5 deg s, and a dynamic range exceeding 1.5 times 10 to the power of 13, all within a form factor of approximately 12 to 15 kilograms and 30 W. Brief description of the drawings. Fig 1, cross-sectional view of the BBG-SVG sensor cell, showing the superfluid He2 Dewar, quantized vortex line, trapped C60 molecule, second sound heater and thermometer array, and the integrated Josephson aperture and DC squid substrate. Fig 2, axial potential energy profile along the vortex axis, illustrating the periodic potential wells generated by the second sound standing wave, with node spacing lambda 2 equals 5 mm and well depth delta U approximately equals 5 times 10 squared J at nominal drive amplitude. Fig 3, system block diagram showing the signal chain from the Josephson weak link through the DC squid, phase lock loop, and parametric transducer interface to the QLAG BEC-MASER network at Lagrange points L1 L5. Detailed description of the preferred embodiment. 1. Vortex formation and fullerene marker. The Sagnac loop is formed by a toroidal or annular superfluid helium-4 chamber with loop radius r equals 5 mm, giving an enclosed area A equals pi r squared equals 7.85 times 10 to the power of 5 m squared. The loop is cooled to 1.5-1.8 K by the QLAG cryogenic bus. A single quantized vortex line is nucleated by rotating the cell through the critical angular velocity and subsequently trapping the vortex by cooling below the onset of vortex annihilation. The vortex core radius A0 approximately equals 0.1 nanometers provides radial confinement equivalent to a harmonic frequency exceeding 10 to the power of 11 Hz. The vortex is therefore radially stable against all anticipated vibration environments. A single C60 molecule is introduced by the helium droplet pickup technique, in which C60 vapor is entrained into a supersonic helium jet before condensation into the reservoir. The molecule migrates to the vortex core because the Bernoulli pressure in the core is lower than the bulk. The energy well depth for trapping is approximately 10 to the power of 8 J, many orders of magnitude above thermal energy at operating temperature. Spectroscopic studies of He-NC60 clusters show a linear wavelength shift of 0.072 nanometers per attached helium atom, with a solvation shell closure at N equals 32 atoms. This provides an in situ optical diagnostic. When the fullerene is correctly seated in the core, the absorption feature shifts by a predictable, reproducible amount relative to bare C60, confirming marker presence without mechanical contact. 2. Second sound axial stabilization. In the absence of axial confinement, Brownian diffusion of the fullerene along the vortex axis would produce position uncertainty exceeding 1 mm at 1.5 K on second-long timescales, generating phase noise that limits ARW. The second sound resonator eliminates this mechanism. Second sound in superfluid helium is a wave in the temperature and entropy field, propagating at a speed c2 approximately equals 20 meters per second at 1.8 k, approximately 10 times slower than ordinary sound. For a resonator of length L equals 10 millimeters, the fundamental standing wave frequency is f1 equals c2 equals 1.0 kHz. Higher modes satisfy Fn equals NF1. The resonator is driven by a thin film heater at one end and monitored by a thermometer at the other, both patterned photolithographically on the cell walls. Driving at temperature amplitude delta T equals 10 mu K generates a superfluid normal fluid counterflow with velocity W approximately equals S delta T, C2 approximately equals 2 millimeters per second. Where ρS, ρN is the superfluid to normal density ratio and S is the specific entropy of He2 at operating temperature. This counterflow couples to the fullerene through the Magnus force interaction, creating a periodic axial potential with well depth delta U approximately equals S delta TVC 60 approximately equals 5 times 10 squared J, equivalent to approximately 50 kBt at 1.5 K. The resulting axial trap frequency is omega z, approximately equals 30 Hz, and the zero-point positional uncertainty is sigma z less than 10 nanometers. The second sound drive thus reduces axial positional uncertainty by more than 5 orders of magnitude compared with the unconfined case, eliminating axial diffusion as a noise source. Because the confinement is provided by a standing acoustic wave and not by any mechanical structure, there is no wear mechanism and no aging of the axial spring constant. 3. Josephson phase readout. Rotation of the loop at angular rate omega about its axis produces a Sagnac phase shift between the two paths of the superfluid order parameter. For a superfluid of atomic mass m He in loop area A, the phase shift is given by the relation dF equals omega A inverting. The rotation rate is obtained as omega equals dF. With m He equals 6.646 times 10 squared to the power of 7 kg and A equals 7.85 times 10 to the power of 5 m squared, the geometric conversion factor H evaluates to 1.01 times 10 to the power of 4 rad s per radian of phase. Thus a phase resolution of dF yields a rotation resolution of do equals 1.01 times 10 to the power of 4 dF radian per second. The Josephson weak link is a 50 to 200 nanometers aperture etched through a silicon nitride membrane spanning the He2 loop. The aperture is sized to support a single quantum of circulation. The weak link is fabricated on the same substrate as the DC squid, which couples inductively to the Josephson current. The squid output frequency V is detected by standard RF phase-sensitive techniques. The QLAG system provides a phase noise floor for the squid of dF approximately equals 1 times 10 radians square root HC. To the power of 9 substituting into the conversion relation gives do equals 1.01 times 10 to the power of 4 times 1 times 10 equals 1.01 times 10 cubed to the power of 9 rad s square root HC. Converting to navigation units, do equals 2.06 times 10 to the power of 8 deg square root hour. This figure represents the phase noise limited ARW floor. Actual performance is expected to be within a factor of 2 of this value after accounting for electronics noise. 4. Dynamic range and maximum rate. The maximum sustainable rotation rate is determined by the vortex critical velocity, the velocity at which the centrifugal force on the trapped fullerene exceeds the vortex pinning force, and the molecule is expelled from the core. The critical velocity is approximately Vc approximately equals kappa equals h approximately equals 25 meters per second, whereas 0 approximately equals 0.1 nanometers is the vortex core radius. For a loop of radius r equals 5 mm, the maximum angular rate before depinning is omega max equals versus c, r equals 25 divided by 0.005 equals 5000 radians per second equals 2.86 times 10 to the power of 5 deg s. The dynamic range is therefore omega max, do approximately equals 5000, approximately equals 5 times 10 to the power of 16 in angular velocity. When expressed as a power ratio in decibels, 20 log 10 approximately equals 315 decibels. The operationally useful dynamic range, referenced to minimum detectable rate, exceeds 263 decibels. This extraordinary range allows the identical device to simultaneously track sidereal rotation and angular rates produced by high-G maneuvers, without range switching or sensor handover. For comparison, navigation-grade ring laser and fiber optic gyros saturate at 300 to 500 deg/s. The BBG-SVG maximum rate exceeds that of the best optical gyros by more than 2 orders of magnitude while simultaneously maintaining a noise floor 4 orders of magnitude lower, a combination not achievable in any prior art. 5. Phase lock to the QLAG BEC-MASER network. The second sound heater drive and the SQUID local oscillator are both referenced to the QLAG BEC-MASER carrier at 6.8 GHz through a divide by n frequency chain with n equals 6.8 times 10 to the power of 6. The parametric coupling between the SQUID output and the MASER carrier uses the interaction Hamiltonian H int equals G disclosed in QLAG section 1.4. Where A and B are the creation operators for the SQUID photon mode and the MASER phonon mode, respectively, and G is the time-varying coupling coefficient. This Hamiltonian implements a phase-preserving beam splitter interaction that transfers the MASER phase coherence to the SQUID readout without collapsing the superfluid macroscopic wave function. The consequence for system performance is that the BBG-SVG inherits the fractional frequency stability of the QLAG MASER array 1 × 10 to the power of 6 at 1000 s integration, without carrying any atomic reference on the vehicle. At Lagrange-point deployments, where the QLAG cryogenic bus is already present, the BBG-SVG requires no additional thermal infrastructure beyond the 1.5 K stage. For vehicle-borne deployment remote from a Lagrange station, the phase lock loop may instead reference a QLAG relay beacon with fractional stability of 10 cubed, still 4 orders of magnitude better than the best space-qualified crystal oscillator. 6. Advantages over prior art. The BBG-SVG does not incrementally improve existing gyros, it changes the operating regime. By using a single C60 molecule as a topological pin for the VORTEX core, the sensor obtains a repeatable quantum reference that does not wander with temperature or aging. There is no mechanical component subject to wear. The VORTEX is a topological object in the quantum fluid, the fullerene marker is held by quantum pressure, and the axial confinement is provided by an acoustic standing wave. Long-term scale factor stability is therefore governed by fundamental constants rather than by materials or alignment. The resonant second sound lattice provides axial confinement without mechanical contact, eliminating the wear and drift mechanisms that limit all optical gyros. The result is a sensor whose performance does not degrade over mission lifetime, a critical requirement for multi-year deep space missions where maintenance access is unavailable. Because the readout is a Josephson phase measurement already phase locked to the QLAG BEC-MASER network, the device inherits a frequency stability of 10 to the power of 6 without carrying its own atomic clock. In system terms, one BBG-SVG replaces the traditional triad of IMU, star tracker, and ultra-stable oscillator for deep space missions, reducing interface complexity and eliminating handover transients that can corrupt navigation state estimates. For high maneuver platforms, the VORTEX critical velocity permits angular rates exceeding 2.8 × 10 to the power of 5 deg/s without saturation, more than 2 orders of magnitude beyond the best optical gyros, while maintaining a noise floor 4 orders of magnitude lower. The result is continuity of navigation through maneuvers that would blind conventional sensors, a capability directly relevant to GPS-denied and contested environments where reacquisition of an external reference is not assured. When deployed as a QLAG terminal, the BBG-SVG does not require an independent frequency standard, thermal enclosure beyond the existing 1.5 K stage, or a separate telemetry link. Total power consumption is approximately 30 W and total mass approximately 12 to 15 kilograms, comparable to a navigation-grade RLG assembly, while delivering stability classically associated with ground-based atomic fountains. For mission operators, this translates to reduced integration complexity, elimination of sensor handover risk, and extended autonomous operation in deep space. 7. Performance summary. Table 1. Performance comparison of BBG-SVG against representative navigation grade optical and cold atom gyros. ARW equals angular random walk. SWAP equals size, weight, and power. Claims. What is claimed is 1. A quantum inertial sensor comprising a superfluid helium-4 reservoir maintained at a temperature below the lambda transition temperature of 2.1768 K. A single quantized vortex line formed within the superfluid, having a circulation quantum kappa equals h per meter He. And a single fullerene molecule selected from the group consisting of C60 and endahedral He at C60, trapped in the core of said vortex line by the Bernoulli pressure gradient of the superfluid flow. 2. The sensor of Claim 1, wherein the superfluid reservoir is maintained at a temperature in the range of 1.5 K to 1.8 K. 3. The sensor of Claim 1. Further comprising a second sound standing wave resonator aligned substantially coaxially with the vortex line. The resonator being driven at a resonance frequency Fn equals Nc2, 2L, where C2 is the second sound velocity in the superfluid helium, L is the resonator cavity length, and N is a positive integer. 4. The sensor of Claim 3. Wherein the second sound resonator has a cavity length L of approximately 10 mm and a fundamental resonance frequency of approximately 1.0 kHz. Producing an axial potential well of depth approximately 5 × 10 squared J and an axial trap frequency of approximately 30 Hz, thereby localizing the fullerene molecule to an axial uncertainty of less than 10 nanometers. 5. The sensor of Claim 3, wherein the second sound drive is phase-locked to a Bose-Einstein condensate-Maser frequency standard having a fractional frequency stability better than 10 to the power of 5. 6. The sensor of Claim 1, further comprising a superfluid Josephson weak-link aperture of 50 to 200 nanometers in diameter, positioned to intersect the vortex line. And a DC squid magnetometer fabricated on a common substrate with the weak link, configured to read the superfluid Josephson phase via the AC Josephson effect, thereby transducing rotation into an electrical signal. 7. The sensor of Claim 6. Wherein the squid output is coupled to a Bose-Einstein condensate-Maser carrier frequency via a parametric transducer having an interaction Hamiltonian H int equals G. As disclosed in the QLAG co-pending application, providing phase-preserving quantum coupling between the superfluid mode and the Maser mode. 8. The sensor of Claim 5. Wherein the Bose-Einstein condensate-Maser frequency standard is located at a Sun-Earth Lagrange-point and the sensor is operated in a force-free gravitational environment at said Lagrange-point. The residual acceleration at said point being less than 10 to the power of 5 meter per square second. 9. The sensor of Claim 1. Wherein the Sagnac phase shift is given by the relation dF equals omega A. Where omega is the angular rate to be measured and A is the area enclosed by the vortex loop. And wherein the angular rate resolution is dU equals dF, yielding an angular random walk of approximately 2 × 10 to the power of 8 deg square root hour when the squid phase resolution dF is 1 × 10 radians square root hc and the loop radius is 5 mm to the power of 9. 10. The sensor of Claim 1. Wherein a maximum sustainable angular rate omega max equals versus c, r, with critical velocity vc approximately equals h, approximately equals 25 meters per second and loop radius r equals 5 millimeters, yields omega max approximately equals 5000 radians per second equals 2.86 × 10 to the power of 5 deg s, providing a dynamic range exceeding 1.5 × 10 to the power of 13. 11. A method of inertial navigation comprising providing the sensor of Claim 7. Phase locking the sensor to a network of Lagrange-point Bose-Einstein condensate-Maser stations. Measuring the Josephson phase difference dF equals omega A at the Josephson weak link, and computing an absolute angular rate omega independent of Earth-based tracking or GPS signals. 12. The method of Claim 11, further comprising verifying the presence and axial position of the fullerene marker by monitoring the herein C60 cluster absorption wavelength shift of 0.072 nanometers per attached helium atom at the N equals 32 helium shell closure. 13. The method of Claim 11, wherein navigation continuity is maintained through angular maneuvers up to 2.86 times 10 to the power of 5 deg-s without sensor saturation, range switching, or external reference reacquisition. Abstract. A quantum inertial sensor comprises a superfluid helium-4 loop maintained below the lambda transition. A single quantized vortex line with a single C60 fullerene molecule trapped in the vortex core as a topological phase marker. A resonant second sound standing wave cavity providing axial confinement of the fullerene to less than 10 nanometers without mechanical contact, and an integrated superfluid Josephson junction and DC squid for rotation readout. The squid output is phase-locked to the QLAG BEC-MASER network via a parametric transducer, conferring fractional frequency stability of 10 to the power of 6 without a vehicle-borne atomic clock. The sensor achieves an angular random walk of approximately 2 times 10 to the power of 8 deg square root hour. Bias stability below 1 times 10 deg per hour. DC to 1 kHz bandwidth. And a maximum sustainable rate of 2.86 times 10 to the power of 5 deg-s at a to the power of 9 mass of approximately 12 to 15 kilograms and power consumption of approximately 30 W, enabling autonomous deep space navigation and high maneuver guidance in GPS-denied environments.